Hello, dear students. Myself, Professor N. Barhate, Department of Chemistry, Dr. Anna Sahib G.D. Bandade, Mahila Mahadal, Jalgaon. Today I am discussing about the topic that is the coordination chemistry. In the coordination chemistry, first we have to discuss about coordination compound. The coordination compounds are those compounds, that is addition molecular compounds, which retain their identity in the solid state as well as in a liquid state. Now, in these compounds, the central metal atom or a ion is linked or joined by means of a ligand or a molecules with a coordinate bond. That is, the central metal ion is surrounded by the number of coordinate bond which are formed from the ligands. For example, if we take the example of this coordination compound, it is nothing but the potassium ferrocyanide. In this potassium ferrocyanide, the central metal ion is the ion, that is Fe plus 2, and this Fe plus 2 ion is surrounded by a 6 cyanide ligands by means of the coordinate bond. So, therefore, the cyanide ions forming a coordinate bond with the ion metal ion by a number of 6 coordinate bond. So, therefore, this 6 number shows the coordination number of the central metal ion Fe. And in this complex compound, the central metal ion is a atom or ion is the Fe, while the cyanide are the ligands, and the number of cyanide ligands shows the coordination number of this central metal ion Fe, while the potassium ion is the counter ion, and the species which is space in the square bracket, it is called as a coordinate sphere or the inner coordination sphere. We are discussing about a double salt. It is also the addition molecular compounds which are stable in solid state but dissociated into constituent ion in the solution. That is, when you prepare a solution of this double salt, then their constituent are dissociated into their ions. For example, if we take the example of the Mohr salt, that is ferrous ammonium sulfate. So, when this ferrous ammonium sulfate we are dissolved in a water, so it will be dissociated into the ferrous ion as well as ammonium ion as well as the sulfate ion. It means in this dissolution of the ferrous ammonium sulfate, it can give the test for its constituent ion, and therefore, this is the physical change. There is no formation of a new compound take place here, while in case of the coordination compound, there is a formation of a chemical change. That is when we can dissolve the ferrous ammonium sulfate in a suitable solvent, it does not give test for its constituent ion, and that is the main difference in between the double salt as well as the coordination compounds. Now, we have to discuss about the terms related to the coordination compound. Now, the one of the first important term is nothing but the complex ion. It is also called as coordination entity. Now, the complex ion is the electrically charged species, either it can possessing a positive or a negative charge, and in this species the central metal atom or ion is surrounded by a number of ions, that is called as ligand or a neutral molecules. Now, when this complex ion possessing a positive charge or it can carries a positive charge, it is called as cationic complex identity, while when it can possessing a negative charge, so at that time it is called as anionic complex entity. The example of this positive and negative complex entity, for the positive complex entity, it is nothing but the tetramine platinum plus 2 complex ion, while for the anionic complex entity, the hexacyano ferrate plus 2 ion. Now, the second term is the central atom or ion. Now, the atom or ion to which a fixed number of ions or a groups are bonds, that is called as a central atom or ion, and is also referred as a Levy's acid, because the ligand can donate the electron pair to this central metal ion, and therefore, it is called as the Levy's acid. For example, if you take the example of one of the coordination compound, that is tetraico dichloronickelate 2. In this complex ion, the nickel is the central metal ion and it is generally transition elements or a inner transition elements. Now, the third term is the ligand. Ligand is the electron donated species, that is either it is a ion or a molecule, and it is bound to the central atom in the coordination entity, that is the in a coordination complex ion. So, these may be charge or a neutral, while the ligands are having a different types. So, therefore, now we are to discussing about the different types of the ligands. Now, the first type of the ligand is the unidentate or a monodentate ligands. In short, we can say that monodentate ligand is the species which having a one donor site, that is it can be joined to the central metal ion from the one side. So, that is we can say that the ligand bounds to the metal ion through a single donor site. For example, there are number of examples of this monodentate ligand. If we consider the example of halogens or a water molecules, ammonia molecule, etc., these are the examples of the a monodentate ligands. While the second type of the ligand is didentate ligands, which have a two donor sites, that is it can join to the metal ion from the two sides, therefore, it is called as bidentate ligands. Now, the third ligand is the polydentate or the multidentate ligands. These ligands have a several donor sites, that is it having two or more donor sites, and it can join to the metal ion from the two or more sides, therefore, it is called as multidentate ligands, and the best example of this is a Idite ligand. Now, we are discussing about the third types of the ligand, that is called as ambidentate ligands. These are the ligands, these are also a monodentate ligands, and but the difference is that in these ligands which can ligate through two different sites. For example, if we consider the example of a ONO, that is the nitrate ion. So, it can be joined to the metal ion either from a left hand oxygen or from the right hand oxygen. So, therefore, such a ligands are called as ambidentate ligands. Now, the fifth type of the ligand is the chelating ligands. The bidentate or the polydentate ligands, which are attached to the same central metal ion through two or more donor atom and forming a ring structure, such a ligands are called as the chelating ligands. That is, in the another way we can say that the multidentate ligands which are joined to the central metal ion more than two sides and forming a heterocyclic ring, that is called as a chelating ligands. Now, in case of this, the ligands can join to the metal ion from the different side and forming a metal chelates, while the process of formation of such a chelate is called as chelation. Now, the more number of chelate rings, more is the stability of the complex, and the stabilization of the coordination compounds due to chelation, it is known as the chelate effect. We are discussing about the fourth term, that is called as the coordination number. It is defined as the number of coordinate bond formed by the central metal atom with a ligands. It means how many number of bonds formed by the ligands by the ligands around the central metal ion. So, that is that number shows a coordination number of that metal ion. For example, if we take the example of hexachloroplatinum plus 2 ion, in this complex ion there are 6 chloride ligands. So, they can forming a 6 coordinate bond around the central platinum atom, and therefore, the coordination number of this platinum atom or a ion is a 6. Now, in case of monodentate ligand, the coordination number is equal to the number of ligand, but in case of the polydentate ligand, the coordination number is equal to the number of ligands into denticity. Now, we have to discuss about the next term, that is the coordination sphere. Now, in case of this coordination sphere, the central ion and the ligand attached to it are enclosed in square bracket, which is known as a coordination sphere. The ionizable group return outside the bracket, and it is known as a counter ion. For example, if you take the example of potassium ferrocyanide, in case of this potassium ferrocyanide, the potassium ions are placed outside the square bracket and therefore, these are the counter ion, while the species, that is the complex ion, that is the Fe(CN)6. So, it will be placed into a square bracket. So, it is called as a coordination sphere or a inner sphere of coordination. Now, we have to discuss about this next term, that is the oxidation number of the central atom. The charge of the complex, if all the ligands are removed along with the electron pairs that are share with the central atom, it is called as the oxidation number of the central atom. For example, if we consider the example of tetracyano copper plus 3 complex ion, the oxidation number of the copper is +1 and it is represented as copper +1. We are discussing about the IUPAC naming system of the coordination or the complex compound. The naming is based on the set of rules given by the IUPAC system. So, now we have to discuss about the rules which are given by the IUPAC system one by one. Now, the first rule is that is the name of the compound is written in two parts. That the first part is nothing but the name of the cation, while the second one is the name of the anion. This is the first rule. That is, the cation should be named first and then anion should be named laterally. Now, the second rule is that the cation is named first in the both positively as well as the negatively charged coordination complexes. Now, the third rule is the dissimilar ligands are named in alphabetical order before the name of central metal atom or ion. Now, the fourth rule is that for more than one similar ligand, the prefixes, that is the di, tri, tetra, etc. are added before its name. So, if di, tri, etc. already appears in the complex, then instead of di, tri, tetra, we have to use the word, that is the bis, tris, tetrakis, etc. respectively are used. Now, the fifth rule is that if the complex part is anionic, the name of the central metal ion is ends with suffix ate. For example, if you take the example of potassium ferrocyanide, in case of this potassium ferrocyanide, the complex part is anionic. So, therefore, the name of the metal ion, that is the central metal ion Fe or ion, it is end with ferrate +2, ferrate 2. The sixth rule is that is the name of the anionic ligands is end in O, while the name of the positive ligands are ends with IUM and the name of the neutral ligands remains as such. But exceptions are there in the neutral ligands, that is we can use for a water ligand or water molecules, that is aqua. For a amine, for a NH3 we have used amine, as well as for the carbon monoxide we can use carbonyl, etc. Now, we have to discuss about next rule, that is the oxidation state for the metal ion. That is the oxidation state for the metal in cation, anion or a neutral coordination compound, it is indicated by a Roman numeral in a parenthesis. That is, the oxidation state of the metal ion is written after naming the metal ion in a parenthesis after its name. Now, the next rule is the name of the complex part is written always in the one word. Now, the next rule is that is if the complex ion is cation, then the name of the name of the complex compound is written as same as the element. Now, the next rule is that the neutral complex molecule is named similar to that of the complex cation. If the complex ion is cation, the metal ion is named same as the element, while the next rule is that is the neutral complex molecule is named similar to that of the complex cation. Now, we are considering some of the examples of the nomenclature of coordination compounds. Now, first example is A, nothing but the triaco, triamine chromium +3 chloride. So, this is the example of the coordination compound, while the second example is a potassium ferrocyanide. This is potassium ferrocyanide is the trivial name of this compound, but if we consider the name of this compound according to the IUPAC system, it is nothing but the potassium hexacyanoferrate 2. Okay. So, now we are discussing about the next point, that is the isomerism in coordination compound. The coordination compounds exhibit the following type of the isomerism. That is, the first one is the structural isomerism and second is the geometrical isomerism. Today we are discussing about only the structural isomerism. So, in this structural isomerism, isomers have different bonding pattern, and on the basis of that it will be divided into different types, such as first, that is the linkage isomerism. This type of isomerism is shown by the coordination compounds having a ambidentate ligand. For example, that is pentaamine nitro cobalt 3 chlorides. So, this is the example of this a linkage isomerism, and in this example the ligands, the nitrate ligands is the ambidentate ligands, that is it having two modes of attachment to the same metal ion, and therefore this compound can be also written as, that is pentaamine nitrito cobalt 3 chloride or pentaamine nitrito N cobalt 3 chloride or pentaamine nitrito O cobalt 3 chloride. Okay. Coordination isomerism, the next is, it is the next type of the structural isomerism. This type of isomerism arises from the interchange of ligand between the cationic and the anionic complexes of the different metal ions present in a complex. If we consider the example of this coordination isomerism, that is the hexaamine chromium plus 3 complex as well as hexacyano cobalt plus 3 complex ion, minus 3 complex ion, and the coordination isomerism of this complex is that is there is a interchange of the ligand take place in between these both, and therefore the after the coordination isomerism the compound is written as, that is hexaamine cobalt plus 3 and hexacyano chromium minus 3 ion. Now, the third type of the ionization isomerism is that is this isomerism arises due to the exchange of ionizable ions with the anionic ligands, and the last type of this structural isomerism is the solvent isomerism. This isomerism is also called as a hydrate isomerism, and in this isomerism water is taken as a solvent. So, it has a different number of water molecules in the coordination sphere as well as the outside the coordination sphere. For example, if you take the example of the this isomerism, that is hexa echo cobalt plus 3 chloride. Now, in case of this compound, if we replace the 6 water molecule by means of a 5 water molecules, and if we inside a one of the chloride ion in the square bracket, so it can forming the compound that is a tetra echo dichloro cobalt 3 chloride, and outside the square bracket also the 2 water molecules are present. So, in this way this type of the isomerism can be formed. We have to discuss about the next term, that is the effective atomic number, that is called as in short EAN. This EAN is defined as the total number of electrons associated with the central metal ion in a complex compound, including those gained by it in bonding, that is called as a effective atomic number of that metal ion. Now, in the formation of the complex, the metal ion will accept the electron from the ligand until the total number of the electrons associated with the central metal ion is equal to the atomic number of the next inert gas, and this concept was proposed by the Sedgwick. Now, in a complex, if we are to determine the EAN of the central metal ion of the complex, so it can be determined by using the formula, that is the EAN of the metal ion is equal to the total number of electrons present in it, and therefore that is EAN is equal to Z minus N plus 2 into Cn, where Z is nothing but the atomic number of the metal atom while small n is nothing but the number of metal or the number of electron loss in the cation formation, and Cn is nothing but the coordination number of the complex or the central metal ion in that complex. We are discussing about the Warner's coordination theory. Now, the coordination compound were known in the 18th century, and it was a mystery for the chemists of those days to understand as to why a stable salt like cobalt chloride react with varying number of the stable molecules or the compounds such as ammonia to give a several new compounds, that is cobalt chloride 6 ammonia and cobalt chloride 5 ammonia and cobalt chloride 4 ammonia. And what are their structures? We do not know. So, therefore, these compounds differ from each other in their chloride ion reactivity, and the conductivity measurements on solution of this compound shows that the number of ions present in solution for each compounds are different. Several theories are proposed, but none could satisfactorily explain all observable properties of these compounds, and similar other series of compounds which had been prepared by then. It was only in 1893 that was Warner put forth a set of ideas which are known as Warner coordination theory, and to explain, which is useful to explain the nature of bonding in the complexes as well as to determine the structure of the compounds. And his theory has been a guiding principle in inorganic chemistry in the concept of valency. Now, we are discussing about the main points or the postulates of the Warner's theory. The first postulate of the Warner's theory is that the metal exists in the complex compound having a two types of the valency. That is, first one is called as the primary valency, it is the ionizable valency, while the second is called as a secondary valency, it is the non-ionizable valency. Now, this primary or ionizable valency is satisfied by a negative ions, only negative ions, and corresponds to the oxidation state of the metal atom or ion, while the secondary valency, it is called as also a non-ionizable valency, which is satisfied by either a negative ion or a positive ions or a neutral molecules, and is equal to the coordination number of metal ion. Now, every metal tends to satisfy these both types of the valency. The second assumption is that is the secondary valency is directed toward a fixed position in the space. It means this has spatial arrangement corresponding to the different coordination numbers. For example, the complexes having, that is the cobalt 3 hexaamine as well as cobalt trichloride pentaamine and cobalt trichloride tetraamine, the number of ionizable ions in these complexes are 3, 2 and 1 respectively. So, it has been proved that by precipitation reaction as well as the conductivity measurements, and the precipitation reaction shows that for the first compound we have obtaining a precipitate, it has a weight 3 grams, while for the second compounds the weight of the precipitate is 2 grams, and the third compounds the weight of the precipitate is a 1 gram. So, that shows that the chloride ions which are present in the outside of the square brackets are 3, 2, 1 respectively. Now, on the basis of Warner's postulates, these compounds then as formulated as, that is hexaamine cobalt 3 chlorides. In case of this, the species which are placed in a square bracket, it is the complex ion, that is the CONH36, and outside the square bracket the species is 3 chloride ions, while the second compound that is the cobalt ion as well as the 5 ammonia molecules and one of the chloride ions is placed in a square bracket, while outside the square bracket there are 2 chloride ions, and in the third compounds 4 amine molecules, 2 chloride ions as well as the cobalt ion are placed in a square bracket, and only 1 chloride ion is outside the square bracket. Therefore, we are obtaining a precipitate in a weight that is the 3, 2 and 1 gram respectively for these compounds, and the species inside in the square bracket being the complex ion and outside the square bracket is nothing but the ionizable ions. So, in this way on the basis of this Warner's theory, the structure of this structure of the compound according to the Warner's theory, it is nothing but for a second compound, that is pentamine chloro cobalt 3 chloride, and in this compound the 3 chloride ions are satisfy both primary as well as the secondary valencies. Okay. Thank you.